think we should just go.
Yeah. So, okay, so thanks a lot, Samson, for the great introduction. Well, and thanks for giving me the chance to give this talk and to be here. So that's a great environment. I hope that I will learn lots of things, and I hope that I will contribute to the discussion during these 4 months, in fact. Okay, that's my talk. So that's the last talk of the day. So I guess it's supposed to be a lecture, so pedagogical material. I hope I will be able to convey some of the information which is in the slides. So that's my goal. Okay, that's a picture of onion. It's nothing special, so just a way to say that when you think about quantum physics is between two different things. So one thing is classical mechanics, the physics of Galileo, Newton, so physics of objects around us, and which is the core of the onion. And then outside the quantum physics, there is something else which we call non-signaling theories. Samson already told us about this topic, and these may be some theories that do not describe physical reality and are science fiction in a way. And so you say, okay, why we should work with something that is science fiction and is not in the physical world? Because maybe this can help us to understand exactly where quantum physics is and what are the salient aspects of quantum physics. And during this talk, I would like to attempt convincing you that indeed this is useful and it is important to single out quantum physics, and with the hope that we could identify what are the features, what are the ingredients for quantum advantage. Meaning we use quantum mechanics in a number of applications like cryptography, computing, communication. Maybe by looking at this picture we can learn what are the salient features of quantum mechanics that are useful in applications. Okay, this is a slide from Samson's talk, and just to show that he did already tell us about this topic, and he did tell us about a hierarchy of empirical models with classical mechanics, quantum mechanics, and non-signaling theories. So, yeah, okay. So.
Stand him on his side.
Right. So the spirit of the talk is combinatorial. So I will talk mostly about graphs and quantities related to graphs. In fact, let me start with a theorem which goes under the name of sandwich theorem. I have a few definitions, and you will see that everything is very much straightforward, if not trivial from the definition point of view. Okay, so I will consider graphs as combinatorial objects, so objects that are composed by vertices, for me 1 to up to n, and edges, which are just unordered pairs of vertices. These are called simple graphs, okay? And I define what an orthogonal representation of a graph is. This is an assignment of vectors, and of course I use this notation here that appeared already, I guess, these days. These are just unit complex vectors in some Hilbert space, and are column vectors of norm 1. So I assign vectors to the vertices of the graph, such that if two vectors corresponding to vertices I and j are, so that they give this inner product equals 0 if they're orthogonal, then the vertices are adjacent.
If they are adjacent, then no?
Yes. So if the vertices are adjacent, then the vectors have inner product 0. So they're orthogonal. Yeah. And here is all I need in order to define a number set to graphs, which is called a Lovász number, which is denoted by theta of g, and this is the maximum as of the sum between 1 and n is the number of vertices of the graph. This is the modulo square of this inner product between the elements of an orthogonal representation and some vector psi, which is a fiducial vector. And the optimization here is done over all the orthogonal representations of the graph and the fiducial vectors. And also D here essentially is a part of the problem. So I'm optimizing over everything here. Now, what is important about this quantity is that it can be approximated efficiently. So this is not a hard quantity to compute. In fact, there is a semi-definite program for approximating these arbitrarily efficiently. Okay, and please.
What happens if you just multiply all vectors by 2? Wouldn't this quantity be unbounded? What do you mean unit vectors?
Yeah, of course, these are unit vectors. These are cats, yes. Yeah, okay. So now the important point about this quantity is that, and here is where the name sandwich theorem is. Now this quantity was introduced by Lovász in '79, and there is a very nice review about this topic in Knuth '94. This was the first issue, first volume of Electronic Journal of Combinatorics, first paper in fact, which says the following. The Lovász number is sandwiched between the independence number of a graph and the chromatic number of the complement of the graph. So here, let me remind you a second, just for the sake of being all on the same frequency, what the independence number and the chromatic number are. Independence number, you look at vertices of the graph, and you want the largest set of vertices, none two of which are connected with each other. That the sets are called independent set. Independence number is the size of the largest independent set, and the chromatic number is defined as the minimum number of colors you need in order to color the vertices of the graph, such that every two vertices that are adjacent have a different color. And of course, the complement of a graph simply is taking the non-edges as edges and the edges as non-edges. Okay. Now, these two quantities, alpha of G and chi of G bar, are hard to compute, untractable. But instead, the Lovász function, Lovász number, it's easy to compute. So we may say, okay, this quantity here can be useful to bound these other quantities. Unfortunately, it's not always the case, because you could construct some graphs for which the independence number is 2, but then the Lovász number is pretty large, as you can see. So somehow it's not great tool for approximating precisely these other quantities. But I will use it during the talk. Okay, and this remark here is it's an old remark. Now, I didn't include a reference directly. At the end of the talk, there will be a page with the relevant references. Fine, so here is an example, classical example, C5. So a graph with 5 vertices, a cycle, and in fact denoted as C5. This is the fiducial vector, so it's like an umbrella. In R3, here I associate vectors to the vertices. I didn't write down the vectors for this specific example, but you have to trust me that I can choose vectors in such a way that I can get this modular square of the inner product equal to 1 over square root of 5, so that the Lovász number for this graph specifically is going to be square root of 5. This will appear later on. Okay, now, after this, let me tell you about a game that we play with graphs, where the Lovász number will have a role when we will consider the game itself and quantum mechanics. So here is the game. So you have 2 players, A and B, which stands for Alice and Bob, and a referee, R. The game goes as follows. Alice, Bob, and the referee get together. They choose a graph G, and the game is made of rounds. At each round, the referee chooses 2 vertices of this graph and send 1 vertex to Alice, let's say vertex A, and 1 vertex to Bob, vertex J. Okay? So, but there is a promise. These vertices can be either the same vertex, or they can be adjacent vertices. So it's immaterial when the vertices are non-adjacent. The referee will not take vertices that are non-adjacent. Now, what do Alice and Bob need to do? They will receive a vertex each, and they have to send back a color each. They color the vertices that they receive. But now they have to satisfy some constraint. If they receive the same vertex, they have to answer back the same color. If they receive adjacent vertices, they have to answer back different colors, with a constraint that they cannot talk to each other. So they get together with the referees, they choose the graph, they can do their strategy, but then they move apart, they can't talk to each other, they would like to play this game and win at every round. Now, here is the question. What is the minimum number of colors such that Alice and Bob answer correctly at every round? So here I wrote the answer to this question upside down, but you may guess it pretty quickly, I guess, right? So when they get together, they get the graph, they color it in a piece of paper. When they go away, they just look at the color, they don't have to talk on the phone with each other, and they receive their vertex, they send back their color, right? So this is the minimum number of colors that they need, the chromatic number. Now, here we go into quantum mechanics. Now, suppose we want to play this game, but we can have access to quantum mechanical resources. I hope that here I will be clear in what I'm saying and will not be too disjoint from what we have seen already in the lectures of Samson. So imagine that for each vertex, Alice has a C-outcome quantum experiment that she can conduct. Essentially, she can measure. She can apply this operator to some vector, okay? So, and the same is for Bob. Now, indeed, this means that for each pair of vertices I and J, there are measurement operators. Here, these are sets of operators, which are projection of finite-dimensional spaces, HA and HB, such that they resolve the identity. So the sum over the projectors corresponding to each vertex, and here the sum is taken over the colors, A1 up to C, B1 up to C, is the identity. And then they have a unit vector, which would be essentially the state of a quantum mechanical system that they share, right? Which is here, I denoted by eta. Eta, which is indeed the state of bipartite system, so is in a Hilbert space HA tensor HP. And there is some kind of setup in which Alice has her measurement devices, Bob has his measurement devices, and the state that they share. Okay, now, suppose that Alice and Bob have access to this machinery. What can they do? Here is what happened. I would like to define this quantity, which is called quantum chromatic number. And it goes as follows. So when Alice performs experiment I, so Alice receives vertex I, okay? She performs an experiment. And Bob receives vertex J, their probability of outcome A and B is given by this. Now, forget about all the quantum mechanics. This is a mathematical expression. So you have your vector, your inner product of operators, matrices, okay, applied to your vector. This is the measurement. Now, this kind of expression gives rise to some matrices, okay? Because I have graph, which is n by n, I have my colors, C colors. So here I define the set of nc by nc matrices obtained by letting the operators and the vectors vary as I want. And this is the set, just the notation, Q, Q, and C. This is called the set of quantum correlations. So every time they play, they define some set of matrices in this way. And here is the definition. The quantum chromatic number will be the least integer, C, such that there is a matrix in this set of quantum correlation with the following properties. And here you see that is exactly what corresponds to the rules of the game. Now, the probability that when they receive the same vertex, they answer different colors must be 0. And the probability that when they receive different vertices, that they answer the same color must be 0. So we are interested in matrices in quantum correlations that have these properties specifically, and the quantum chromatic number is the least integer for which there are matrices that satisfy this property here. Okay, so as a matter of fact, now there is this theorem, which is a collection of several results about the quantum chromatic number. These results are the following. First of all, this quantity is not easy to compute. But maybe we have to go to this point first. So the quantum chromatic number is always upper bounded by the standard chromatic number, and lower bounded here, I look at the lowest number of the complement, of course, because I wanted to put the chromatic number here, it's the roof of this. So the quantum chromatic number is sandwiched between these two quantities, and unfortunately is not easy to compute. Okay? So meaning that maybe I cannot really use it to bound the chromatic number. Despite the fact we don't know if in general it's going to be, if you take a random graph, for example, where does the quantum chromatic number stay. Now there is a special case which is called the rank 1 case, where for these projectors, for the operators that Alice and Bob choose, I just choose unitary matrices. This is sort of, instead than taking orthogonal representations, I blow them up. So instead of taking a vector for each vertex, I take matrices for each vertex. And I would like that there is a constraint that is, if I take for each two vertices I and j, a matrix associated to I, matrix associated to j, and this is the transpose conjugate of ui. So if you look at the diagonal entries of this product, this has to be 0. This just reflects the condition that I expressed before, whenever I and j are adjacent. And now you could just ask what is the minimum dimension of these matrices, and this tells you the value of the rank 1 quantum chromatic number. So this quantity is related to Kochen-SPECKER sets, a topic that has been mentioned very briefly by Samson, but will be reconsidered again in the lecture of tomorrow or Friday. And is related to a famous open problem in algebra, which is the Kohn embedding conjecture, which has to do with von Neumann algebras. Indeed, if you are interested specifically in this problem, I suggest you to give a look at the paper by Paulsen and co-authors. I will give the exact reference at the end of the talk. Please.
So the quantum chromatic number, you say it's NP complete. Is it, we know strong non-approximability results for chromatic number. Do we know strong non-approximability results for quantum chromatic number?
No, we don't. Yeah. Yeah, it would be interesting to know something about that. Okay, so why I wanted to introduce this topic? Because again, here I am in a kind of sandwich, and before I mentioned the sandwich theorem here, you can you have more layers, then you can look at some kind of club sandwich where you have not just one layer but more than one layer in the middle, and here you have the chromatic number. Here you have the clique number, which is just it's like the independence number, but for the complement. Okay, and here you have the lowest theta function, the lowest theta number. So quantum theory, for at least for this kind of game that I described, is here. So between the lowest number and the chromatic number.
Where is the rank 1?
It's still up here. It's still above. Okay. So now, people among you that are familiar with the lowest number may have already guessed that I was going to talk about the Shannon capacity, because the lowest number was introduced by Lovatz in '79, specifically to approach a problem which is in information theory, which is computing the Shannon capacity of a graph. So I will define what this quantity here is. Is a graph theoretic quantity which was defined by by Shannon back to 1956 in the context of zero-error information theory. And here I give the definitions of this quantity, and I would like to tell you just in a single slide where quantum mechanics fits this picture and how this topic again is related to this onion that I mentioned at the beginning of the talk. So let us define a channel as a stochastic matrix, which gives the probability that if you have an alphabet with symbols 1 up to n, the ij entry of this matrix is the probability that symbol I is received when symbol j is transmitted. So this is classically called a channel or a stationary channel. Now, with every channel, you can associate a graph, which is called confusability graph of the channel, and again, here the vertices will be the symbols of the channel, and there is an edge if two symbols are confusable when they are transmitted by the channel. And here is definition of single shot or one shot zero capacity, which I denote as C0 of the graph, because in the end, if I'm interested only in not in the probability that symbols are confused, but that they are confusable or not, then I can forget about the channel and just consider the confusability graph, and what would correspond to the capacity of a channel when you use the channel only once, the one-shot zero capacity. So this is the maximum number of symbols that can be transmitted without confusion when you use the channel once. And you see, just 1 minute of thoughts shows you that this is equal exactly to the independence number of the graph, because this is exactly the largest set that gives you this property here. Now, of course, we can do coding, so meaning we can send words, not just symbols. So, for example, now I'm composing words, so I'm coding. And in order to move from the single shot situation to the asymptotic situation, I would like to encode code words into the vertices of a graph. How do I do that? I look at something which is called strong graph product. So if you take two graphs G and H, the strong graph product of G and H as vertex set equal to the Cartesian product of the vertex sets of the two graphs, and then there is an edge in the new graph if and only if some conditions are satisfied. So specifically, there is an edge here, the two-ordered pairs are the Cartesian products, ij, kl, if and only if ik is an edge of the first graph and j equal l, or jl is an edge of the second graph and I is equal to k. So this is a way to define the strong product. Now, if I'm interested in this quantity in the asymptotic limit, I will look at the limit for the strong product of a graph with itself going to infinity. Now this turns out to be equal to the sup, and here is 1 over k log. This is just for information theoretic point of view of the independence number of the strong graph product of the graph G with itself, k times. This is doing coding, and the Shannon capacity is defined indeed in this way, and I denote it as C of G, the graph. And here is a theorem which stays, so this theorem is due to Lovász, 79. It says that the Lovász number is an upper bound to the Shannon capacity, which is an important point. Why? Because now here, I guess, I'm in company of many logicians, so this quantity here is not even known to be computable. Now, if you ask, is the Lovász number a good approximation for the Shannon capacity? Well, we don't know. We know that there are cases in which this is the same, and we know also many cases in which this is different. So we know cases in which the Lovász number is strictly larger than the Shannon capacity.
Question.
Please.
So in the one-shot case, it was kind of clear what the intuition for that measure is. But what is, from a kind of information theoretic point of view, what is Shannon capacity measuring? I mean,
yeah, exactly the same. The number of code words, right, asymptotically, that can be sent without confusion. Yeah, and of course in the zero error setting. So the intuition here is my mistake, because I should have probably put a picture of this strong product, at least for code words of length 2. You would see that the vertices of the graph are labeled by code words, and if two code words are not confusable, then they are not connected. And this gives you, in a way, some intuition about what happens here. So now this is an important fact that you see. It's the Shannon capacity is only upper bounded by the lowest theta. And if you like to see examples of this fact, there is a nice paper by Emmert's 1979 that uses some combinatorial matrix theory quantity, which sometimes now is called as Emmert's rank bound, which usually is no better than the Lova's number, but there are some cases in which it is a bit better and is still an upper bound to the Shannon capacity. Okay, now said this, let me go to the quantum side of the story. Now, before the talk, I asked Samson, should I include some review of quantum mechanics, and so it's your responsibility now if I put this slide full of so, but I think it's useful. It's useful because in a way or another we will have to discuss these topics hopefully during this next few weeks. So it's good if I remind you of this. Quantum states and operations. So systems in quantum mechanics composed by two parties are represented by some space of this type. This is an Hilbert space, right? So this is usually the space associated with a party which is called Alice. This is a space with a party which is usually called Bob, and M are just the dimensions of the two spaces. Now, if you take a Hermitian matrix rho, I say AB, which will be in fact on the total space, on the space of both parties, such that the trace of rho AB is equal 1, and rho AB is positive semi-definite, so this is a state of the system. Now you say, okay, why this should be the case? This is axiomatic. When von Neumann and friends decided to cook up quantum mechanics, they somehow forced us to use this approach. Now, if this is the best approach in the universe, we don't know, but unfortunately, we are bound to use it at the moment, unless of course we use some other constructions that do not use quantum mechanics in Hilbert space. So each state, so each matrix here is a convex combination of one-dimensional projectors, and here again this is just a column vector in the Hilbert space, and this is the adjoint conjugate of this, which is a row vector, onto subspaces of this type. Okay, so this is just a outer product. So if we cannot write a density matrix in this form as essentially a sum of tensor products, okay, where these omega I, these are just real numbers that sum up to 1, then we say that this rho AB is entangled. It's just terminology, okay? So if you cannot decompose this matrix as a convex sum of tensor product with some weights, this is entangled. And what is a projective measurement? Now you look at one of these states, and I want to extract some information out of it. So I cannot just take an entry of the matrix and pull it out. Yeah, I can do it mathematically, but then when I go into the physical world, I need to use some kind of mathematical machinery which is reflected by what we can do in a laboratory. And measurements are implemented by projectors, in fact projective measurements, such that if you take two projectors I and j, so this is Kronecker delta, That's what you get, and the sum of those is 1. Now, when a measurement, there's a typo, is carried out on a state psi, the result is obtained with probability pi, and this is the probability, here is the projector, and the state is forced in some post-measurement state, which is given here. Now, a quantum channel is just a map that takes states into states, and is expressed by Hermitian operators, such that the sum of these products is equal to the identity. So this is essentially all that one needs to know about quantum mechanics to deal with lots of interesting things, and of course to deal with this part of the talk. Now, I've mentioned these layers, so classical, quantum, non-signally. I pointed out that there are some games where you can see pretty well that quantum mechanics give you some kind of, let's say, advantage, if you really like. What would be the advantage of this quantum chromatic number? That if you want to convince a referee that the number of colors is more than the chromatic number, sometimes you can actually do it because of the game. But of course, it's no concrete advantage, it's an extremely ad hoc. So here, instead, by using a framework which is not dissimilar from what I already said, you can actually see some type of quantum advantage, and you can see a clear example of the fact that quantum mechanics will be between classical physics and non-signaling theories. And now I have a few definitions to give. Now, take a graph again, and consider the graph partitioned into k cliques. So cliques are just fully connected subgraphs, and these k cliques will have size d, each of them, b1, b2, pk. Now, let us label each vertex with ordered pairs, where q will tell you which clique, and I will tell you which element, which vertex in the clique. Now, we say, this is a definition, we say that G realizes a KOCHEN-SPECKER set if it has an orthogonal representation. And here I label the vectors in this orthogonal representation as I label the vertices of dimension d, and G does not have a k clique, right? A clique of size k, where k was the number of these cliques, such that each vertex from this clique belong to one of the k cliques. So whenever you have a graph that can be partitioned into the cliques with this property, then you say that the graph realizes a KOCHEN-SPECKER set. Now, it is important to observe that whenever a graph realizes a KOCHEN-SPECKER set, and this is a theorem, then the independence number of the graph is going to be strictly smaller than k, where k here is equal to the number of cliques of the partition. And of course, since we said that the independence number of the graph is equal to the one-shot zero-error capacity of the graph, then I just write C0G smaller, strictly smaller than k. Now, going back to the information theoretic framework, I have a sender. Now my sender is Alice, and I have a receiver. My receiver is Bob. Here we don't play a game, but Alice and Bob send information through a classical channel, so they will have this stochastic matrix, but they work in the zero-error framework. Now, what if the sender Alice and the receiver B share a unit vector as before, this vector eta, and each Alice and Bob can perform measurements on their parties of their vector and their subsystems. And now we can define two quantities. We can define the one-shot or single-shot entanglement-assisted zero-error capacity, whenever this vector here could be, for example, an entangled state, Q0 of G, and the entanglement-assisted Shannon capacity or entanglement-assisted zero capacity Q of G, which will be two quantities defined exactly as before. One is the single shot, one is in asymptotic limit. However, the difference is that now Alice and Bob have access to this state, and they can measure, and they can send each other information by the classical channel, but having available this state. So here there is a theorem which I want proof. In fact, there are several statements here, but it's sufficient to give you a feeling about, again, this onion structure. One can show that the one-shot entanglement-assisted zero-error capacity can be in some cases larger than the one-shot zero-error capacity. So meaning that there is a quantum version of the independence number that sometimes is strictly larger, in fact, than the independence number of a graph. And this is, again, a graph theoretic quantity because we are dealing with a classical channel, and the only thing that we have here is this is access to some entanglement. Now, second result, and here is a version of sandwich theorem again. So here is the Shannon capacity. Here is the Lovász theta number. We can prove that the entanglement-assisted Shannon capacity is between these two numbers. Okay? So what is the meaning of this? That if we want to upper bound the entanglement-assisted Shannon capacity, we can, again, compute the Lovász number. And so we can upper bound this efficiently. Now, we know that the Shannon capacity can be strictly smaller than the Lovász theta. And here we have a quantity that is between them. So it is plausible to conjecture, in fact, that the Lovász theta is a quantum mechanical quantity. And in fact, is plausible to conjecture that the entanglement-assisted Shannon capacity is always equal to the Lovász theta. But we don't know that. This is an open problem. What is important is that there are graphs for which the Shannon capacity is smaller than the entanglement-assisted Shannon capacity. So meaning that by using some quantum mechanical resources, we can increase the capacity of classical channels in certain cases. So meaning that we have some kind of quantum advantage. People today speak often about the idea of quantum supremacy. What does it mean that quantum mechanics allow you to do certain things that you cannot do classically and that gain some advantage in the real world? Of course, this is sort of artificial still because don't use this very much. Well, there are some protocols, for example, related to index coding that use zero-error capacities, and maybe this would suggest that if we do index coding in the quantum regime, we may have some advantage in terms of having larger capacity for channels. Yeah, okay, so this is yet another situation in which quantum mechanics appear to be in between two different objects, one which would be classical and then something else. And here is the if you really like, I guess the slide will be online later anyhow. This is slides that's been taken from a talk of Will Matthews. This is a protocol that shows how to implement this communication for entanglement-assisted zero-error capacity. But it's not important for us to go look at this now. Now. Let me go on with another situation which is somehow closer to what we have heard during the lectures of Samson, which is contextuality. Contextuality, again, it's a framework in which we can see that where quantum mechanics is especially in between classical mechanics and non-signaling theories, and here I would like to give a feeling about that by using some combinatorial situation. So contextuality, so it's about measuring, right? It's about asking questions to physical systems, and what does mean measuring? Measuring indeed is asking question, right? So in a way, this reminds a bit of this Wheeler doctrine of the fact that the universe is participatory, right? So reality is sort of created by us asking questions about reality. And so here, let me give you the very basic picture of contextuality in order to deal with that when we consider a combinatorial framework. So a context is nothing but a set of mutually compatible questions. So questions that can be asked without mutual disturbance. So here it's a card, right? So here are two questions, Q1 and Q2. Now is the color red? A1, the answer is yes. Is the suit diamonds? And the answer A2 is yes. So you can ask these two questions without mutual disturbance, right? So this is a context. So now, non-contextuality, what does it mean? That answers should not depend on context, right? So let us look at these blue boxes here. Q1 and Q2, two questions, a context, and Q2 and Q3, two questions, another context. So non-contextuality simply means that answer to Q1 is yes, answer to Q2 is yes when I ask Q1 and Q2 together, and answer to Q2 is less, answer to Q3 is no, and when I ask Q2 and Q3 together, so the answer of Q2 is the same, independently whether I ask it together with Q1 or Q3. Yeah, and so this means that I have non-contextuality here. Now, a compatibility structure will be a set of questions and organized into contexts. And I can construct an hypergraph from this. Now, for the purpose of this talk, I will just construct some graphs. So here, I have three questions that form a context, 2, 3, and 4, and three questions that form another context, 1, 2, and 5. So I connect together questions that belong to the same context. So in this way, I construct a graph. Now here you see I have 2 clicks, of course. And here is a little bit of everything I want to say about contextuality in the last 2 slides. Consider a compatibility structure formed by 5 questions, and each 2 of those adjacent form a context. So Q1, Q2 is a context, Q2, Q3 is a context, and so on. This is a pentagon, like C5, this cycle with 5 vertices that I considered before. Now, what exclusiveness means that I could ask questions and I impose the constraint that answers to adjacent questions are not both 1. So if Q1 is 1, then Q2 cannot be 1, so must be 0. Q5 must be 0 as well. Then Q3, okay, can be 1 again, but then Q4 must be 0. So you see that I can do this again. You know, Q3, okay, let's say is 1, so this can be 0, 0, 0, 0, so at most 1. Q3 can be 1, this is 0, this can be 1, but this 0 is 0, so this is, the sum is 2. So this is what I'm doing. I'm working with classical physics, right? So and in classical theories, the answer 1 have expectation at most 2, if non-contextual and exclusive. And this is the independence number of C5 for this specific compatibility structure. That's very simple to see. Now, suppose that I move to a different regime where I am not interested in the fact that answers to adjacent questions are both 1, but probabilities of answers, where answers do not depend on context, but probabilities of answer do not depend on context. So, and this is the situation of non-signaling theories. And here I have, again, the compatibility structure with probabilities P1, P2, P3, P4, and P5. Now, exclusiveness here will mean that for each context, the sum of the probabilities must be 1. And here, I explained, with a diagram what it means that probability of answers do not depend on context. You have question 1, the probability yes is A, question 2, probability yes is B, question 3, probability yes is C, and if you ask question 2 together with question 1 or with question 3, the probability is always B, independently of the context. So, now, this is, as I said, related to non-signaling theories. So the answer 1 have expectation at most 2.5. So this is simple to see because you can put half for each of those. So it's half times 5. So if non-contextual and exclusive. Now, what is the maximum that you obtain for this? This is called fractional Packing number. Now, it's again a combinatorial parameter. How is defined? So you associate a number between 0 and 1 to every vertex, then you want that the sum overall click is at most 1, and then you can see that you end up with something like this. You can solve this with linear programming. Okay, so what about quantum mechanics? Again, I look at my compatibility structure. Now I'm going to ask questions, and question here is measuring some state of a physical system, and the measurements will be implemented by my projectors, which are given by vector v1, v2, v3, v4, v5, and the probability, yes, will be given by this modulo square of the inner product as we have seen. And what would be the expectation now? Well, the expectation will be assigning this vector in such a way they form an orthogonal representation, and what we have seen before, we can get the max for that, which is square root of phi, which is equal to the Lovász number of the cycle C5. So this can be generalized, in fact, for any compatibility structure, and it turns out that if you want to compute the let's say the amount of contextuality of a compatibility structure in quantum mechanics, then you get the Lovász theta function. Exactly. So this is not a bound, but is indeed the exact value of the contextuality. And now, of course, as a remark here, the compatibility is given by this fact. Now we have then some type of classification theorem. So if you look at, no, I can forget about hypergraph, but if you look at a graph which is obtained by connecting contextual questions, the maximum expectation values for exclusive answer in the three physical theories, which is classical mechanics, non-signaling theories, and quantum mechanics, are given exactly by these three quantities, which is very nice. And now here, if you look at the vectors that correspond to this expectation value, and these are the sets of these vectors, you can see this inclusion diagram. This is, of course, is well known, but what this theorem would say is that the maximum for each of these is given by these three quantities, which is interesting. Now, interesting because, of course, there is a way that it gives you a way to see which compatibility structures have quantum mechanical behavior when considering contextuality, which is different from classical behavior and different from these non-signaling theories, and you can play with all the combinatorics that are available in this framework. Now, in the perspective of thinking about quantum mechanics as what we said at the beginning, thinking as quantum mechanics in this region, and in the attempt to understand what are the salient features of quantum mechanics, one may look at these combinatorial structures, because maybe in the attempt of determining what are the ingredients that make quantum computation possibly advantageous with respect to classical computation for certain problems, maybe we could look at contextuality, for example, and see try to identify certain situations in which contextuality may be in fact an important ingredient for advantage of quantum computation. Now, one interesting fact which I like to observe is that, specifically about the Lovász number, there are some families of graphs that are called perfect graphs, for which the Lovász number is equal to the independence number, equal to the let's say Lovász numbers of the complement is equal to the clique number and equal to the chromatic number, and these perfect graphs are graphs for which indeed the first and third number are the same for all the induced subgraphs. So we know that for perfect graphs, many problems that are hard in general are going to be easy. indeed, computing the clique number, it's easy because of the fact that the Lovász number is equal to that. So it means that for perfect graphs, these three sets correspond. They're just one, right? So then maybe it's plausible to start thinking about the possibility that there is also a notion of, let's say, of quantum perfect graphs. So there will be certain type of graphs for which certain computational problems are going to be easy because there will be some parameters here that are the same. And maybe if we think about quantum complexity classes as being if we think about this quantum complexity class as BQP, right, which is an analog of BPP as supposed to be larger than BPP. So in that perspective, maybe there would be some problems that are going to be easier if you use quantum mechanics instead of just using probabilistic computation. And maybe by looking at some parameters inside this universe here may suggest something. It may suggest where the power of quantum computation is. And so I guess. Okay, this is of course a speculation, right? But it's nice to think that on one side contextuality, on the other side information transmission, which has some advantage, and maybe also computation, maybe different sides of the same object, where if there is some quantum advantage, then maybe the ingredient for this quantum advantage is the same, and no matter which context, which situation we are looking at, if it's communication, if it's computation, if it is something like this. Yeah, I think more or less this is my talk. Okay, so thanks.
You show the references, you said that.
Yeah. So it's, from the psychological point of view, it's an excuse for you to read them.
Yeah. Perhaps you can, if you post the slides, then...
yeah, they will be automatically there. Yeah,
could I ask a question?
Of course, yeah.
You began with this kind of sandwich with the three quantities, and you said the two outside ones are hard to compute. The middle one, the Lovász number, is easy to compute. But when we look at the sets of correlations, then it seems that the situation is reversed, because the inside and outside are polytopes, so they're kind of easy to test. And the middle one, as we were discussing earlier today, we don't even know if it's computable.
Yeah.
So do you have any concern, way of thinking about that?
Yeah, so this EQ essentially is the first level of this hierarchy, this SDP hierarchy. So if you look at quantum correlations, now there are certain cases like the CHSH situation where here you reach the upper bound, so you can get Sealson bound. But there will be lots of inequalities out there where this is still very far. In fact, indeed, this corresponds to the first level of the SDP hierarchy of Pironio, Asina, Vasquez, or Lasserre hierarchy, so SDP. Yeah, so meaning that this is not very useful to compute quantum correlations.
Do you have any thought about why the difficulty seems to be inverted in this?
Right.
That's an intriguing point, I think.
Yeah, I don't have much intuition about this. Yeah. Please.
So in the security community, there is this concern about one-shot security versus multiple. And you mentioned those ideas, but there it turns out the Renyi entropy, or the min entropy, is a useful measure. I'm wondering if there's any role for something like that in this.
So I know that there are some entropies defined for graphs, defined combinatorially. However, not much work has been done in that perspective in the quantum setting. But Yeah, no, I'm not sure if I'm talking about something completely or talking to what you mentioned, but there is space for, of course, for looking at different types of entropies and possibly define different type of capacities which are associated to entropies. Please.
This maybe was already part of your answer to the Samson's question, but are either of those two quantities, Q0G or QG, known to be computable?
No, we don't.
So even Q0G, you don't know that?
Yeah. So, of course, my hope would be that one could prove that QG is exactly equal to the Lovász theta function. And so you see you have classical physics, and well, here is classical information theory, so zero error capacity. Sometimes there is a gap. And actually, to try to understand this gap it's a difficult problem because the behavior of the independence number of a graph with respect to the strong product is very erratic. There is a paper by Alon and his former student Lubetsky, which shows that indeed, if you look at the independence number of strong graph products, it's a bit wild. Now the hope is that quantum mechanics instead makes things nice, and that indeed the entanglement assisted Shannon capacity is exactly equal to the Lovász theta function, which would give a neat operational interpretation of the Lovász theta function as a physical quantity, because so far for the Shannon capacity is just an upper bound, so nobody tells you that has anything to do with information theory, right?
Another question. So since you don't know how to compute this Q, so Q of G, so how did you come up with something that separates CG?
Yeah. So I guess that would be a separate talk with the proof for this, which, for example, this separation here is given in a nice paper, which I'm sorry when I scanned, because I didn't make these slides on the computer, I made it by hand, but then I scanned it upstairs and stupidly I didn't notice that not everything is in the slide. So this cryptic information is Liung, so which actually I put in the references. So they proved this result by using the Emmert's bound. So there is a rank bound, which is a combinatorial matrix theory quantity, which is an upper bound to the Shannon capacity. In most cases is larger than the Lovász theta number, but in some cases is smaller. Interesting that the paper on this topic came out immediately after Lovász paper, upper bound in the Shannon capacity. So you can use that bound for certain graphs which are constructed from some combinatorial objects, from some root systems, okay, and show specifically that the Emmert's bound is between these two quantities. Actually, so far, all the examples, all the computable examples of QG are exactly equal to the Lovász theta function. So we don't have, of course, we have that's in fact the conjecture. So what they did was having a family of graphs for which this is equal to the Lovász theta function, and knowing that for this family of graphs, the rank bound is between the Lovász theta function and C of G.
It's open even for C7, right?
Pardon?
The QG is not known even for C7 for
Yes, yeah. Yeah, indeed, it's a mysterious quantity. And the hope is that instead QG will be easy because of quantum mechanics.
I'm not even sure that the question makes sense, but I'll try it. It's late in the day. In the morning, Samson raised this problem of recognizing which systems are quantum realizable. is it conceivable that by looking at parameters like this, we will have a sequence of parameters that will enable us to differentiate quantum realizable from non-quantum realizable? I'm thinking of something like the homomorphism numbers that Lovász considered that characterize a graph uniquely up to isomorphism.
Yeah, it's quite a beautiful question, actually. Yeah. So I think that Samson has more grip on this topic than me. I think to give an answer that would make some sense. But I think that the question actually is quite deep, and
Yes, I agree.
and indeed you suggest something which would be very much worth discussing these days, I think.